All right, CNT120, Chapter 1. We're now in the section on topologies. So with the topologies, if we remember a little bit of the history that I mentioned earlier, and I'll fill some gaps in, some of these will start making more sense. Otherwise, they look very out of place. One of the first ones they mention is our bus topology. Now, this is actually a picture of a bus topology, but you're like, okay, I don't quite see and understand what's going on. Well, first Ethernet networks, and that's kind of why I had this here, the first Ethernet networks, this was Xerox's answer to a network, was a bus topology where they used a coax, single coax cable that the devices and network would tap into. It was just one giant shared cable that they would tap into, the coax cable. And the users would send data out across that cable, and if it was, as the data moved along the network, it was for me, I would hold on to it. If it wasn't, I would get rid of it. And this was the solution for Xerox to make the network to share their data around. So here, this is the kind of the brainchild behind Ethernet, Bob Metcalf. This was his first concept drawing for Ethernet, where here was this coax bus, and they're even showing that you would tap into it. Basically, a transceiver would bolt around the cable and connect into my computer, and this acts as like my network card, if you will, to get data in and out of the network. The very first ones used this transceiver that would bolt around a thick coax cable. This was your 10-base-5 Ethernet. It's thicker than what you have at home. And this transceiver would bolt around and tap into the network. And the cable would go from the computer NIC into there, and that acted as your connection in and out of the network. That slowly evolved into using thinner coax, thinner than what you have at home, 10-base-2, and they moved on to, instead of tapping in, they used these little T connectors, BNC T connectors. And the T connector would connect to the back of your computer to the network card, and then they'd use another coax cable to go from computer to computer. Then the T connector would connect in, then go from computer to computer. So either way, if you redrew these into a simplified form, you literally have these computers tapping into this central coax bus. So this is what you have. All these computers tapped into the central coax bus. And when computer A here, if you will, wants to send data over here to computer B, if you will, this data goes out in the network, and there's nothing there to act as a traffic cop. That data literally goes to everybody. And computer A, when they sent their data over here to computer B is like, thanks, appreciate it. Everybody else still gets it, but they're like, well, it's not for me, and they throw it away. They treat it like junk mail. They throw it away. So this was a way to get data from computer to computer, but it was not very efficient. Okay, it was relatively expensive, but it did not scale well. It was difficult to troubleshoot because you don't have those link lights or anything on those connections to know if it's connected or not. And it was not very fault tolerant. If you had a loose connection, the whole network might not work correctly. That was Xerox's solution to building a network. At the same time, you have people like IBM, like we said before, developing network for their computers to move their data around. Well, IBM developed what's called the token ring topology. The ring topology. Again, if you look at this picture, you're like, oh yeah, I see a circle there, okay. But if you're like me and most normal people are like, well, I don't understand how you get that. Well, let me show you. What they did was they connected the device together in kind of like a circular fashion, and a token got shipped out on the network. Token is an empty data frame. Think of it almost like a shuttle bus driving around the city. That empty data frame gets put onto the network, and as it circles, it starts looping the network just like a shuttle bus driving around the city. When a computer wants to send anything, they grab a hold of that, put the data in, and that circles the network till it gets to the destination and delivers it. And then it keeps circling like a shuttle bus, picking up people and dropping them off, picking up people and dropping them off. So this was an active topology where you're connecting computer to computer to computer. Well, how it actually got done was they would use this device here called an MAU, Multi-Station Access Unit. All the devices would plug into it. But when you look at this, you're like, well, that doesn't look like a ring. But what's actually happening is that token gets passed out to a computer and back. Then out to another computer and back. Out to another computer and back. Out to another computer and back, and it loops around. So if you follow that, it's literally going computer to computer to computer to computer. And if I start mapping that, I end up with a circle. I end up with a ring. Hence I get this. Hence the token ring topology. And that was IBM's solution to connecting computers together to make a network. Okay. Other manufacturers were doing similar things. They were making their own way to connect their own computers together. So back in the 80s, we had some computers that were using the bus topology, and we had some computers using the ring topology to connect them together. As time moved on, okay, we'll go back here to Ethernet. Ethernet started developing and evolving, and it's moved into or migrated into a star topology. So star topology, I now have a single connection going to every computer. I'm not tapping in. Before we were all tapping into one central coax bus here, if you will. We now have a central device, and there's a cable running to each computer individually. So they started migrating away from the bus and moved to the star. Each computer now gets connected, instead of using coax cable, using twisted pair, which is what we use now. Each computer connects into this central device using a twisted pair connection. So now I have each device connected individually. So if I have an issue with one, it does not affect the others. Unlike here, if I had an issue with one, it might affect the whole network. Okay, so I'm getting an advantage already. And let's look here. This showing your individual connection here, individual connection here, individual connection. Okay, and you now get this as your topology. This kind of, if you look at it carefully, each one is going individually, so it does look like this right here, like a star. Okay. Now, with the star topology, I get some fault tolerance. Again, if one device, if there's an issue with this cable here, it does not affect anybody else, because this is the connectivity device in the middle. It is flexible. I can add and remove people very easily. Before, with that bus, if I remove somebody, it might break the whole network. Here I can add and remove people easily. I also start getting things like link lights for troubleshooting. I literally get a link light above each port to let you know, yes, it is on, or no, there's no link, so I don't have a connection here. Something's not right. I actually have some of that to help with my troubleshooting. The disadvantage is I do need more cable now, because I literally need a cable to every computer. So I'm going to use a lot more cable. And I also do have single points of failure, which they're going to mention, I think like chapter 2, they're going to talk about that a little bit. But if I look here, actually I'll use this picture. If I look here, if this thing fails, whole network's done. That's what they mean by that. That's what they mean by single point of failure. So initially, with our star topology, they used a hub in the middle. And now we're talking the 90s. The 90s, you were using hubs to connect your networks together. And initially, how the hub worked, if computer A sent data in, computer A went to send data to another computer, as it moves into the hub is what they call layer 1. It is not able to do any traffic control. It literally repeats that data out every single port to everybody in the network. So functionally speaking, it's working just like the bus topology before. It doesn't function any differently. But I get the advantage of it, as we said here, I have link lights for the ports. Each one is an individual connection. Okay, so I have those advantages, but functionally it's going to work the same way. And that's your hub. This is actually a picture of a hub. We used to have these in our lab room many years ago. And it literally just repeats the message out to everybody. So it's a big old shared environment. You're sharing all the bandwidth. Well, along comes, and this is early 2000s now, along comes switches. Early 2000s, places were migrating out their hubs and putting in switches. Switches are a layer 2 device, which again we'll talk about with the OSI model. Layer 2 now has some intelligence. It can actually read MAC addresses, that's a layer 2 address, and maintain those in a table. And the idea is when once it learns those, which it actually learns pretty quickly, once it learns those, when computer A wants to send data to computer B, the switch gets it and goes, hold on, I know where computer B is, and it only sends it out the port to computer B. It doesn't send it to everybody. So now I have a lot more throughput because I'm not sharing with everybody. All because the switch is a layer 2, it's reading those MAC addresses and putting them in a table so it can send data out a single port, not all the ports. And again, what that allows you to do is, computer A sends to B, it sends right there. Well, I can also have computer C sending data to computer D over here at the same time. I can get more dedicated throughput, and as they show here, you can have multiple conversations happening simultaneously. And here's an example of a switch. This is similar to what we have in our lab room. Each has its own connection. You have a link light. I can add, remove. I have traffic control, so I can get data to each individual node, if you will, so I can have multiple conversations simultaneously through the switch at the same time. And that is kind of where we are now. This type of star topology Ethernet network with a switch in the middle that's doing this traffic control for us. That's kind of how we've evolved. That's where we are now. Okay, and there's some different types of switches that would do the job for us. There is such a thing as a mesh topology. Well, mesh topology, I'm not going to, and I purposely picked this picture. I don't have computers here. I'm more than likely mesh topology. I'm connecting different networks together. Think about HACS campuses, Harrisburg, Lancaster, Lebanon, York, Gettysburg. When I need to connect those together, if I only have one connection between Harrisburg and Gettysburg, if that fails, we're done. So what you do is you start doing most likely a partial mesh. There might be a connection from Harrisburg to Gettysburg, but then Gettysburg might also connect to York. So if the connection from Harrisburg to Gettysburg fails, the traffic might go Gettysburg to York to Harrisburg and still get to Harrisburg. That would be at least a partial mesh topology, backup routes. Full mesh is very expensive because you're having all these individual connections that you're renting, if you will, or buying or putting in. Many places at least do a partial mesh, so you have some redundant connections. That is your mesh topology. And I purposely tried to pick pictures that were not computers to get you thinking, connecting the Harrisburg network to the York network, to the Lancaster network, to the Gettysburg network. That kind of idea. That's where you typically see a mesh topology. Yeah, it's going to be more expensive because all those extra connections that you're usually renting or leasing, if you will. Backbone networks, these are the networks that are connecting together, typically your closets or your switches, if you will. These need to be high bandwidth connections. And I give you an example here. If we're running 100 meg to the desktop, the backbone connection needs to be at least a gig to handle all of that, and so forth. These can be copper connections, but they will also often be fiber for distance purposes. The simplest backbone is a daisy chain. I literally just connect switch to switch to switch to switch. This is simple, easy, but it does have a problem of, all this data has to go through here, all this data has to go through here, all this data has to go through here. So it can add some delay and so forth, but it's easy to hook up. That's a simple daisy chain or serial backbone. They also have a distributed backbone. Here I spread it out and I literally have connection between maybe routers, one on each floor or one in each building, if you will. And this adds some traffic control. The router's a layer 3 device. It has more intelligence, so it can do more traffic cop action, if you will. And now I could build in a redundant link between, floor 1 and floor 3. So if I have a failure here, we can still get traffic this way or still get traffic this way. That would be a distributed backbone. It's going to be a little more costly because more equipment involved, but it also adds some security potentially to each floor. There's a collapsed backbone. This gets used pretty frequently. Instead of having all those routers on each floor, I bring them all together to one device. And I'm going to use this example here. This is a book example. I'm going to use this example here. All these switches here connect to a layer 3 switch, which is more intelligent than layer 2. And then that runs through the router here. So there's an individual connection to each floor. So if I have a failure here, it only affects that floor. That's a collapsed backbone. I still do have single points of failure here, but I have an individual connection to each floor, which helps with your bandwidth. And last but not least would be a parallel backbone, where I have redundant connections between my switches, which can be done. I can do 2 connections between the switch here and here, and I can have them configured to work in tandem, if you will. They work together, and so if one fails, the other one's already there running. So if I have a failed link, I still have connection there. That can be a parallel backbone. And this is kind of the extreme example here. I put in redundant layer 3s, redundant routers, but that would